Welcome to this video lecture on Chapter 7.2, regarding momentum. Here we will look at the astounding concept of this baffling phenomenon. Remember to follow along in the textbook as always. It is first important that we look at the system. We deal with two types of forces, the forces that the objects within the system exert on each other, and the external forces that are exerted from outside of the system. Examples of external forces are, for instance, gravity and the force of friction. In an isolated system, the sum of the external forces equals zero and the momentum will therefore be conserved. An application of this can be found in the firing of a cannon. We normally think about the force from the cannon on the bullet, but tend to forget that there also is an equal force exerted on the cannon from the bullet. This follows Newton's third law. Therefore, we will have an equal amount of momentum going in opposite directions after the launch. They will cancel each other, and the final momentum will equal the initial momentum, being zero. Momentum has been conserved. Should drop the bass. Indeed. Here is how one should go about when dealing with momentum. Select a system. Then identify the external and internal forces acting on the system. Then verify that the system is isolated. Momentum is a vector. Set final momentum equal to initial momentum. Look, listen and take notice. Now we will show some real-life applications of the conservation of momentum through the game of pool.
When doing these demonstrations, we will assume that the system is isolated. This is not completely true, but finding a frictionless pool table is very hard. However, you will still be able to see how momentum is conserved. See how momentum is transferred from the white ball to the blue. Final is equal to initial.
Now we have 2 balls, but look! Oh, and 3 balls. The same effect. 4 balls? Even 5 balls. 6 balls. Yeah, let's just take the whole thing. Extraordinary.
Let's now take a look at what happens if we send 2 balls. The momentum going in must equal the momentum going out, and therefore 2 balls will come out. The same effect is found with 3 balls. Marvelous. Momentum is a vector, so it will be conserved in all directions. Fabulous. And now it's problem time. A poor little freshman is standing on a frictionless frozen lake when suddenly Mr. Wolf comes rushing in 10 meters per second. He then grabs the freshman and the two of them continue together straight forward. What will the new speed of Mr. Wolf and the freshman be? Set the final momentum equal to the initial, and the answer will reveal itself. I hope this was helpful, and
if you need some extra time or you have questions, please make sure to write them down in your notebook and bring them to class tomorrow. Thank you very much.